So for section 5.2, we're going to be looking at random variables. A random variable is a variable that has a single numerical value determined by chance for each outcome of a procedure. We'll have two options with this, discrete or continuous, and we've actually seen this idea before, whether something's discrete or continuous. But discrete, finite, are countable. Generally, these are going to all be whole numbers. Versus continuous, the idea is it can be measured on a continuous scale. So when we're talking about time or weight, but the idea is you will have decimals, fractions, and ranges. So I can, ranges of between those decimals. Here's some examples of some random variables, and we're going to discuss whether it's discrete or continuous. So the number of televisions in a household. In this situation, the number of televisions, you could have 0, 1, 2, 3, but the idea is that there are no decimals, fractions, so this is going to be a discrete random variable, right? Number of people who recognize McDonald's brand name. You're not going to have 1.2 people, right? The number of people is discrete. The amount of milk a cow produces in one day. Well, they don't put the milk out ounce by ounce, right? There is a continuous stream or range between or decimal or fraction amount. So this is a random variable that is continuous. The number of girls in a family with 4 children. You could have 0, 1, 2, 3, 4. That is a set amount. It is finite, okay? And they're going to be whole numbers, makes that discrete. Height of a new strain of tomato plants. Well, the height is going to be a range, right? It could be a foot. It probably isn't exactly a foot. We would measure it to the nearest foot, maybe. That could make it discrete, but generally we measure height. We do feet and inches and range in between, and we get those decimals, so that makes that height continuous. Probability distributions we've seen before as well. They give the probability for each value. This should remind you a little bit of our activity that we did. When a basketball shoots 3 free throws, let X represent the number of shots made. Okay, this is discrete. He can make 0, 1, 2, or 3. And here are the probabilities. Okay, they're going to ask, is this a legitimate probability distribution? What does that mean? Well, X has to be a numerical random variable. Check your definition from earlier, right? Each of these is discrete. Each of these is random. They are independent, so we're going to have our probabilities as we go, but that's X is a numerical random variable. That is checked off, okay? I can't have, my favorite color in here. You could do that with probabilities, but then this wouldn't be a probability distribution, okay? This says that the summation of all the probabilities should equal 1. There could be some round off error, but let's check. What is 0.01 plus 0.1 plus 0.38 plus 0.51? Well, that makes 89, 99. That adds up to 1. That makes sense that the sum of the probabilities should equal 1. Don't forget that we could have some round off error, and that is okay. And each probability must range between 0 and 1. So none of these probabilities are negative, right? And this showed up a little bit in the last quiz as well. I had some people mess up on formulas and give me a probability of 1.4. That's utter nonsense, right? You can't have 140% probability. That's all this is saying. So if you can check all 3 of these off, then it is a legitimate probability distribution, okay? And if it's a legitimate probability distribution, then we can find a couple things. The first thing we can find is the mean of these probabilities. The mean of these probabilities will be every X times the probability, X sub I, P sub I. I'll just do this. Come on, erase. This is the problem here. There we go. Times, how about the probability of X? Okay, so every X times its probability, adding them up. So in this situation, that would be 0 times 0.01 times, all right, x is 0 times the probability plus 1 times the probability plus 2 times the probability plus 3 times the probability. Well, this is 0. This is 0.10. Next one should be 0.76. And the last one, 1.53. We can add those up. 0.86, 1.53. Okay, have that open. I don't want to do mental math and end up being wrong. Of course, let me see if I can remember the numbers that I just switched over. Let's see. So 0.86, 1.53, 2.39. So that would be the average, okay? Also known as the expected value. That's not helpful. This thing's tripping out. Let me leave that line there. Okay. Expected value. So we would expect on average 2.39 shots. He's not going to make 2.39 shots, so we would expect between 2 and 3 shots on average. And if you look, notice that's where most of the probabilities are, right? The standard deviation is going to be every x minus the mean, mu this time, okay? And we're going to take that and square them, multiply them by their probabilities, and then add them. That doesn't look like a lot of fun. So I am going to show you this one more time. We'll use our calculator to do this. Every x minus the mean times the probability. It's not too hard. The x's range from 0 to 3. The mean was this 2.39, right? So this will be everything from A bracket minus 2.39. In fact, I could make that even a little easier, because the next thing is to say, well, we don't add them here, right? We got to take all those and square them. So if I put it in parentheses, am I in the wrong spot? Wait a second. All right, up here, if I put it in parentheses, I could take that group and square them at the same time. Same numbers, they're just now squared, right? And then our probabilities, we got to fill in, were 0.01, 0.1. What is your problem? All right. 0.1, 0.38, 0.51. So we can take everything from B, which is every number minus the mean squared, multiply it by the probability. That would be everything in B times everything in C, and add them up. The sum of everything in D. 0.4979. But keep in mind, that is actually not our answer, because at the very end, to get this actually would be our variance. That would be the variance. To get this, I also at the end need to square root that whole mess. So the square root of 0.749, let's do the square root of E1, 1. This will take the cell E1 and square root it, and we got 0.70562. Wouldn't it be nice if the calculator could do some of this heavy lifting for us? Right? Good news. It can. I'm going to create a new sheet because I just like this too much. I think it's too beautiful to make go away. So I'm going to add a new sheet. Put the x's, 0 through 3. The probabilities. .38, .51. And I can run one var stats on a single list. Now this is different because normally we leave frequency list as 1, and I like to leave it as 1. Okay? In fact, if you haven't done the test yet, you probably shouldn't mess with this because I think it might change the default in here. But our X list, our X's are in A, but the probabilities or the frequencies are in B. So we're going to change this time. So our X's are in A, our frequencies are in B. Make sure you go down here and put the results past that in C. Is that the mean we got? 2.39? Is that the standard deviation we got? I don't know. That's weird. Oh, that's undefined because this is for this is the population. This is the true standard deviation from his probabilities. Okay. Is that the standard deviation we got? 0.70562? Hey, look at that. Feeling pretty good about this. So this is not as difficult as you want it to be. You should be able to find the mean every x times its probability, add them up. You should be able to find the standard deviation, but technically this is the standard deviation of a population. Okay, true. So keep that in mind. Find the mean and standard deviation using technology. We just went over it. What this does is it gives you instructions for the TI-83 and 84. Let X be the number of red lights out of 5 signals on the way to work. What values can X take? How many red lights could you hit on the way to work? And you're like, well, when I'm driving, every single freaking one is red, right? But let's say somebody's like, I had the best drive out of all the lights. The lowest you could get would be 0. Keep that in mind. 0 is an actual answer here, right? So you could have 0. You could have 1 red light, 2, 3, 4, and 5. Okay? What values could X take? I could have 0, 1, 2, 3, 4, and 5. Do these values meet the requirements of a probability distribution? Check the X's first. Do these represent a random variable? Well, the number of red lights you hit is random, right? You're driving. There's so many other factors. It's either going to happen or not. It's kind of random, okay? Second requirement. Each of these probabilities should total to 1. Add them up. 30. That would make 65. This would make 70, 80. Did I miss something? Oh. This would make 65. This would make 80. Now we're good. Gosh, I don't know why this is doing this. Then 80 and 15 would make that 95. And then that would make it add up to 1. Probabilities added up, total 1. Check also, all the probabilities must range between 0 and 1. In this situation, all the probabilities range between 0 and 1. Find the mean and standard deviation. It really wouldn't be that hard. I could do this by hand. Like I said, every x times its probability would be 0 plus 0.25 plus, what is that, 0.7 plus 0.45 plus 0.60 plus 0.25. Excuse me. Let's see. 50, 1.1, 1.8. I got 2.25. Oh my lordy. And that should be the mean. Okay. Now, do I want to do the standard deviation by hand? No. But the mean's pretty easy to do, right? Either way, I would recommend you use the technology. I could cheat a little bit and play with this because our numbers range from 0 to 5. So I literally could just update this 4 and 5. Now what's it doing now is it's freaking out over here. Okay, it's freaking out over here because these don't match anymore. The dimensions mismatch. So that's why that 1 bar stat's freaked out. Fill in the probabilities. 0.05, 0.25, 35, 15, and the last two we need is 15 and 5. 15 and 05. And then it has no problem. What's the mean? Is that the mean we got? What's the standard deviation? The true standard deviations are 1.25996, round up to 1.26. Okay. Quick recap on the process on that, because we've only done it once. If I had to rerun this, right? If I had to rerun this, or maybe you didn't type it over like I did, typed it in a new list, how would we do that? Menu, statistics, calculations, one variable statistics, just like we did before, on a single list, but our x's are in A, and our frequencies are in B. And make sure the results are in C. And those should be our same numbers. Okay? Alright. Draw a probability distribution of this. Okay? Well, our x's range between 0, 1, 2, 3, 4, and 5. Okay? Why do I have another notch? Well, what goes right here between 0 and 1 is just the zeros. So the probability ranged from 5% up to, it's like 35. So 1, 2, 3, 4, 5. I don't think I can do 5. I think I need to do 10. So that I can get as high as 35, right? And if you'd like, you can stick a notch in the middle of each one to represent the 5s. So what was the probability there? Of 0 was 0.05. So we make a bar between 0 and 1 that is 0.05. This you read as the zeros. Okay? What goes between the 1 and 2? What was it? 0.25. And that's all the 1s. What goes between 2 and 3? 0.35. And that's for all the 2s. And it's 15, 15, and 5. So it is 15, 15, and 5. And you could stick a 6 here, because the way we read this bar represents all the numbers from starting at 5 up to 6, not counting 6. So this is just all the 5s. So we've drawn a probability distribution before, and it should actually make sense with our mean now of 2.25. Doesn't that look like it would be about the center of our graph? Identifying unusual results. This is not a new definition. We say unusual. We've had, what was it, less than? Let me get a exorcist here, a young priest and an old priest here. Less than 5%. And how do we get that? Well, using the empirical rule, we know that within 2 standard deviations, I hope you're enjoying this because I'm about to have a record of me swearing at my computer. We know that within 2 standard deviations is 95% of the data. So what's left on the outside? The other 5%, really 2.5 on each side, right? But the idea is that we say anything beyond 2 standard deviations would have a probability less than 5%, would be considered unusual. Wendy's manager performed a study to determine the probability distribution, okay? Find the values of the unusual max and unusual min. So that would be the mean plus 2 standard deviations and the mean minus 2 standard deviations. I need to figure out some information on this. I need the mean and the standard deviation. So 0 through 12, I'll do a new one this time. 0 through 12. And our probabilities were 0.011, 0.035, 0.089, 0.15, 0.186, 0.172, 132, 0.098, only about halfway, bugger, where are we at? 0.063, 0.035, okay, 0.019, 0.004, and last but not least, 0.006. Just a quick recap. Is this a legitimate probability distribution? Do all of these numbers represent a random option, right? This is the number of people waiting. It's random, right? They're independent from each other. They're going to show up or not. It's a random occurrence, and these are the probabilities of this occurring, okay? Second, do these probabilities add up to 1? Well, I can verify that pretty easily. What is the sum of everything in B? Well, that feels pretty good. And all the probabilities range between 0 and 1. Okay? What do we need? Menu. Statistics, one variable stats. Our X was in A. Our frequency was in B. And results are fine in C. What do I need for this? I need the mean, 4.87. So that's our mean. And our standard deviation, which is 2.229. So 4.87 plus 2 standard deviations would be 4.87 plus 2 times 2.229, 9.328, and the mean minus would be 4.87 minus 2 times 2.229 so change that from a plus to a minus 0.0 or 0.412. So what would be considered unusual? Anything out of this range. Okay, this would be 0.412 and 9.328. Those would be all of the usual. So what's unusual? Anything outside of that range, like 0. Anything past 9, like 10 through 12. So using this rule, we would consider 0 and 10 through 12 are considered unusual. I'm not even going to mess with it. Okay? Would you consider it unusual to flip a coin 500 times and only get 247 tails? Well, we could calculate the probability of this, right? What is the probability that we get 247 tails out of 500? Okay? Well, we know that the probability of getting, tails is 1/2. So we would expect, if there were 500 times, that our expected value would be 1/2 times 500. So we would expect 250, right? Is 247 far away from that? No, this would not be unusual, okay? How do we calculate that specifically? We're going to do that in future sections, okay? That's going to be coming up. That's called a binomial distribution, okay? But if the number of successes is less than 5%, right? Or if we do beyond there and it's 5%, then we would call that unusual. Let's use these numbers and show us how we'd answer these, okay? Is it unusual to have only 2 people waiting in line? Well, based on our example, what is the probability of x equaling 2? Well, 0.089. Is that less than 5%? No, it is not. It's not less than 0.05. So it is not unusual using our probability rules. That's not helpful. Using probability would 10 be unusually high? Well, the probability of 10 is 0.019. So the probability of 10, that would be less than 0.05. So 10 itself would be but I don't think that's what they're asking here. They're saying, would 10 be unusually high? Okay, so what they're kind of saying here is, would we expect, right, 10 or more? That would be kind of a different question. So I'm not sure. I'd try to be a little clearer on this, but what if we did this? Is 10 unusually high? Would we expect more than 10? I wouldn't word it this way, but they may. Then I would take these 3 probabilities and I would add them. So that would be 10, 11, or 12. So that would be the 0.019 plus 0.004 plus 0.006. And that would add up to 0.029, which is still unusual. So 10 itself is individually unusual, and 10 or more is still considered unusual. Okay? We talked about expected value already. Every x times its probability. This is also the mean of our distribution. Roll a die. If the side that comes up is odd, you win $1, equivalent to that side. If it is even, you lose $4. Let x represent your winnings and construct a probability distribution. Okay? So what are our outcomes? Well, x can be even or odd, right? So x, we could get a, rolling a die, we could get a 1 through 6. No, x is going to be our outcomes. And our outcomes are either you win the value if it is odd. So that means I could win $1, I could win $3, I could win $5. Why didn't I list the 2, 4, 6? Because the 2, 4, 6, the outcome is we lose $4. List the outcomes. What is the probability? Well, what's the probability that I win $1? 1 out of 6. What's the probability I win $3? Well, if I roll a 3, that's also 1 out of 6. What's the probability I win a 5? 1 out of 6. What's the probability I lose $4? 3 out of 6, or 1/2. How would I get the expected value? Every x times their probability. 1 times 1/6 plus 3 times 1/6 plus 5 times 1/6 minus 4 times 1/2. So if I play this game, I expect to get 1/6, 3/6, 5/6, and that is 2, right? So 4 9/6, or 1.5, I expect if I play this game to lose 50 cents, right? I take every x, every outcome. The reason we list the odds separately is because they each have a different outcome. 1 wins $1, 3 wins $3, 5 wins $5. Those are 3 outcomes. The 4th outcome is that we lose all $4, and that's for all the evens. Okay? We take every x, multiply them by the probability, add them up. We expect to lose 50 cents. You throw a dart to break a balloon. You win $100 if you break the balloon. If it costs $5 to play and you're willing to spend $20 to win, construct a probability distribution to find the expected value. Expect there is a 10% chance of hitting the balloon on each throw. What are our outcomes? Well, I'm going to throw it how many times? 4 throws. How do we know that? Well, $5 times 4 throws, right? Is the $20 that we have to play the game. Take the $20 divided by the 5, we got 4 throws, right? What are all the possible outcomes that could happen? Well, I could win all 4. I won $400. Sort of. It cost me $20 to play the game. So I didn't really win $400. I won 400 minus the 20. I won $380. Okay? What if I only won 3 of them? Well, that would be win, loss, 300, win nothing, still cost me $20, That would mean I would win 280. What if I only won 2? I'd win 200. I'd pay 20. What if I only won 1? I won 100. I paid 20. And what if I lost every throw? I'd lose 20 bucks. So this is looking good so far. There's a lot of opportunities for me to win, right? These are just our outcomes. What is the probability of X occurring? What's the probability of 4 wins? What's the probability of 3 wins, of 2 wins, of 1 win? Okay, here's the issue. I'm looking at this, and how are we going to calculate these probabilities is actually more than I want to do at this point. We will save this question until we do binomial distributions, because that will make these probabilities easier to calculate, and we will deal with that in a later section. Okay? So we'll save this question. We'll come back to it when we get to the binomial distributions. This last one's pretty easy. Certain policy costs $100. It pays $10,000 for a major injury, $3,000 for a minor. The insurance company estimates that 1 in every 2,000 policyholders will suffer a major injury. 1 in every 500 will suffer a minor. Construct a probability distribution for their profit. Okay? What are our outcomes? I could buy the policy, and I could get paid $10,000. Very exciting. Here's a problem. I don't really get $10,000 because I already paid $100. So my expected on that would be 10,000 minus 100. I would basically be earning $9,900. Or I could have a minor injury. Congratulations, right? You get paid $3,000 to cover that. Issue is, you already paid him $100. Or you don't suffer any injuries. You get paid nothing. That's okay, because you're covering your butt, right? And you paid yourself, you paid him $100. So you basically lost $100 getting this insurance policy. You're trying to play it safe, right? How do I get the probabilities? This is not a big binomial distribution. They're going to give this to us. Look, 1 in every 2,000 suffer a major injury. What's the probability of that major injury? 1 in 2,000. What's the probability of a minor? 1 in 500. And what's the probability of not suffering an injury? Everybody else, right? So that would be 1 minus the 1 over 2,000 minus the 1 over 500. Give them a common denominator. How about 2,000 out of 2,000 minus 1 over 2,000 minus 4 over 2,000. We're looking at 1995. That'd be the rest of them. So there's going to be one person that gets paid for a major, 4 that could get paid for a minor, and the other 1,995 lost $100. How would we get the expected value? Well, 9,900. See if I get some space here. Times the probability. Plus 2,900 times the probability. Plus, let's times it minus, right? 100 times the probability. So let's see what we get. Times 1 out of 2,000 plus 2,900, and that was 1 out of 500, minus 100 and we're expecting everyone else to have that occur. So we expect to lose $89. That means if you're buying this, right, you can expect to lose $89. That means, on average, the company's going to make $89 per person. Okay? That's it. This section shouldn't be too bad. Go ahead and knock it out. We're going to build it. We'll get to the binomials very soon, and we'll build on that.